So as you can see, the theory has a deterministic part, which is the Schrödinger's equation, and the stochastic part, which comes from wave function collapse. So to deal with the stochastic part, we need to remember probability. Some statistics. To do something statistical, for example, if you want to do statistical physics, you first need to know statistics, right? Very simple stuff, not very deep stuff. Let me start with an example. So I have a group of people. Number of people with age 14 is 1, 15 is 1, 16 is 3, 2, 25 is 5. So let's define probability of J. Probability of having a certain age is number of people at that age divided by total number of people from 0 to infinity. Right? So, for example, P16 is 3 over 14. How did I get it? 3 people with age 16 and the total number of people is 14. Easy, right? Now, what do I have here? The sum over J equals to 0 to infinity of Pj is 1. Probability of having any age is 1. Now, let me talk about expectation value. We will use it. So, this is just a fancy name for average. Okay? So, you have a distribution of people with different ages. What is the average value or expectation value of age in general? How would you find it? You would sum J with Nj divided by sum of not J but Nj. In other words, it's sum over from J equals to 0 to infinity probability of being at age J times J. Did you get this? Do you have any objection? This is, if it's perfectly clear, we can continue. All right. For example, turns out if you use this data, expectation value of J is 21. So that's where this word gets, that's where we understand that expectation value is a bad name for an average, right? Because it tells us that the expectation value is 21, so you expect to get 21. However, there is no one who has age of 21. Do you understand it? So although we will say expectation value, we will mean average, right? Okay. Expectation value is average. There is no difference. Just some name that we gave to something, and we will regret it forever. Okay. So, for example, let's find average. Let me just, from now on, I will call it average. But if you, somewhere in literature, you see expectation value, you will remember that it's just average. So, average of J is 21. We could also calculate average of J squared. How would you calculate it? You would sum up j equals to 0 to infinity j squared times pj. Do you agree? Whatever you want to get here, you just plug it in here. Do you want to get j cubed? You plug in j cubed. Say it. Yes, e to the j. You plug in e to the j, right? So you can plug in any, very good example. You can plug it anything you want. Expectation value of j squared is not always expectation value j squared. So there's a difference between expectation values, average of the square and square of the average can be different. They are usually different, right? So actually their difference tells us the variance. Let me just write variance. Variance is defined like this. Variance is basically expectation value of, I will keep repeating this error, I guess. Any j minus average of j. So you find the average of deviations squared. What's going on here? Let me just plot it somehow. So you have some values, right? And there is an average value. What you are finding here with variance is average of these deviations, squares of these deviations. So how spread is the data? How spread out is the data? If you have a sharp data around a certain point, if everyone is 23 years old, then your variance is 0. Okay? If there are babies, elderly, and it's spread out. Okay? So after doing some maths, you can show that j squared, this thing, is actually equal to average of squares minus square of the average. This gives you the variance. Do you have any question? No? And this sigma, so sigma squared is variance, and sigma itself is called standard deviation. All right?
So instead of calculating all data, we can use only this formula.
We can use only what?
The secant formula.
Yes, exactly. You can use the second. We will use the second formula in quantum mechanics. Okay? That's why that's in the box, while the rest is not in the box.
Why there is difference like square?
Why do you,
What does square makes it standard?
why? What makes it? Okay. You are actually genuinely asking. Genuinely asking. Okay. So why do we care not about the square of it, but the square root of it? Because it basically gives, yes, it gives the relevant units, and it basically gives the width of the spread, okay, approximately. So that will correspond to our sigma. Although, is this 2 sigma, or it depends where you put this. It's 2 sigma? Yes. But, okay, doesn't matter. Don't worry. We are not that mathematical, okay? All right. If you have a continuous variable, so let's say you have continuous variable. Then everything that you have seen so far as discrete formula turns into integral. You have seen some summations. Now let's say you have some sort of probability distribution, p of x versus x. If you want to find average of x, you just integrate in the relevant places, let's say from minus infinity to infinity, probability of being at x times dx, provided that the integral of probability is 1. So that's the normalization for the probability, right? Now, why do we care? Because as we have discussed earlier, our wave function squared gives us the probability of being at a certain point, right? So back to quantum mechanics, what does normalization mean for quantum mechanics? It means that integral of the wave function squared, absolute value squared of the wave function, must be 1. Must be 1, and it has to stay 1. Has to stay 1 throughout the dynamics, okay? What does it mean? It means that the Schrödinger's equation that we have seen earlier must be in such a form that this is guaranteed, right? Okay? So, after some math that I used to show to you, but no longer, you can just show by using Schrödinger's equation that the partial derivative of psi xt squared dx is 0. So you can, after so which this here, which involves Schrödinger equation. So you take the structure of the Schrödinger equation. Let's see the Schrödinger equation one more time.
Will it be a homework to prove that?
There will not be a homework to prove this, no. But if you are interested in the proof, it's done in one of the recommended textbooks, which is Griffith's Introduction to Quantum Mechanics. You can follow it. It's very clearly written there. All right? So, very well, we have normalization condition and Schrödinger equation provides that. Well, let's move to something more physical. Ehrenfest's theorem. Ehrenfest's theorem tells you that, well, let me just use average. Average values, but in textbooks it's expectation values, okay? Average values obey classical laws. Obey classical laws. What does it mean? Let me start with an example. Classically, momentum is equal to m times v. Do you agree? So you just put brackets around them, and that's the quantum mechanical correspondence. Okay, on the average of momentum of the particle needs to be mass times the velocity of the particle, average of that. Okay, whatever you get from, as you might remember, we can gather some ideas using wave function, right? So for example, we know that F equals to ma, right? What is F in quantum mechanics? It's del V over del X. Do you agree with this? Potential, the negative derivative of potential. We have written this before. So this is force equals to dP over dt, right? This is classical law, and quantum version is this. Okay? That's, by the way, how you make sure that your new theory fits the old theory. It's always the case that you have a physics theory that works in a domain, and then there are some domains where it stops working, and you don't erase that theory, you build on top of it because it's providing explanation for so many things, right? So, how do we find, for example, expectation value of x? Sorry, average value of x. How would you find it? Like, let me show you, for example, in the probability case, we found it like this, right? Now, what is our probability function? Psi of xt absolute value squared. So, average value of x can be found like this. X, you just plug in x. Whatever you have here, you plug it in. Xt squared dx. Right? Whatever you have here, you plug it in here, and this is probability, right? This is your px. Does it make sense?
What happens if the average value inside the function has a differential equation?
We are coming to that. So, let me write it one more time. So, I can write it like this, by the way. So, I'm just writing this as star times x so I just have rewritten this psi of xt absolute value squared as psi star times psi. Do you have any objection to that? Anyone? No? Everyone is with me? Yes. So, good. So, this is the general version of finding expectation values. Okay? The question is, x is x. That's obvious. What do I put when I have p? Do you understand the question? What do I put there? Can I put p? Yes, but there is a way of doing it. So let me show you what is the way. Here is the way. So what is p, average value? It's m times v, right? So let's simplify it. Do you agree with this? I just have written, instead of v, del x over del t. So let's say mass is not changing, so would you accept this one? Would you accept this one? Yes? Do you have any objection? This is important. So why we are doing this? Because let me rephrase it. So we already know how to get average of x, but we want to get from this knowledge, start from that knowledge and go over here. And what do we use? We use the fact that average value of p is actually related to average value of x. So we can just take the time derivative of this part to get what p is. Does it make sense? So what we need to do is to do this. M times del over del t, and then this whole integral minus infinity to infinity, psi star x psi dx. That's what we need to do. Do you remember we have done something like this before? Over here, right? We did the time derivative of psi squared, right? Now, and do you remember what happened there? We just said that there was some mathematics there involving Schrödinger equation. Yes? We are doing it again. So, now we have this beast, and we are going to write down. So, after some mathematics that involves, again, Schrödinger's equation, we arrive, so we are skipping that bit of mathematics. Where do we arrive? We arrive here. Turns out average value of p is this. You might say there is no h bar. There is no h bar over here. How h bar appeared here? Yes, it comes from Schrödinger's equation.
And also somehow mass is gone.
Is it? Yes, also because of Schrödinger's equation. In Schrödinger's equation, there is also mass there, right? So somehow mass is cancelled, and what we are left with is this. Did you follow so far? Yes.
When you are talking about the average value of pure momentum, is the average value of the momentum of electron in the space in a time? I couldn't understand what's the.
Very good question. Remember, we are doing quantum mechanics, so the main actor is wave function. Okay? We no longer define the system's state in terms of position or momentum. No longer. There's a particle there, and wave function defines everything there is to define about it. Now we want to ask questions. We are classical beings. We want to know where it is. It tells you that you can only know certain things. For example, average of where it can be, right? So you derive the average of its position from wave function. I give you the wave function, you take that information out of the wave function. Again, same wave function also tells you the average. Okay, I think that's why we are using expectation value here, because when I say average, it doesn't feel like.
It seems like you are doing this transferable on a single part.
Yes, so it's expectation value, because what would it come on the average if we did a measurement? That's what it is answering, the expectation value. Yes? When I say average, you lose that the fact that someone is expecting that average, right? Okay, so let's bring back the expectation value term so that it doesn't lead to a confusion. I think that's where it came from, right? What do we mean by average?
Expectation value of the momentum is the expected momentum that we expect to get that value after many experiments. Yes?
We should change actually the word to expected average. Instead of expectation value, what is the expected average of momentum? What is the expected average of position? When you measure position, what's the expected average? Why you are not?
Because you are doing a single measurement, so you cannot talk about average.
You can. I mean, what's the expected average? Like, if you do measurement, what's the expected average? Although you are going to get one result, if you do it on an ensemble of systems with the same wave function, you will get a distribution, and the average of that distribution will be this number.
Actually, there is a nice way, like possibility. First of all, the expectation value is in the middle, but there is no way you can.
Yeah. Okay, we will come to that, definitely. But do you see what just happened? What just happened is that for x, we have something to measure, and there's an operator corresponding to that. So this is the operator corresponding to measurement of x. And we are, okay, this will make much more sense later on if I come to that point, but right now we are looking at everything in x. You could have looked at everything in p as well, but that's really tricky business. It's like looking at something in Fourier domain. Does that make sense to you? Like frequency domain, not frequency domain in this case. I think some of you get this idea, but for now we are concentrated on x. That's why we started with x, and then we derived the operator corresponding to p in the domain of x. And the operator that corresponds to p is this weird looking object. So p in quantum mechanics is h bar over I times del over del x. I will not put the hat because I will then keep forgetting which one has a hat and which one doesn't have a hat. So what is this hat? The hat is that the hat is there. So what Ekin is saying is that there should be a hat here, which would remind ourselves that this is an operator. Okay? But since, as I mentioned earlier, I will keep forgetting about this hat, I will not put hat, and you figure it out whether it's an operator or not. Okay? Yes, you have a question. You wanted to have a hat? Yes?
Because it's some momentum, right?
Mm-hmm.
The other thing is operator, so you confuse me, but now I got it.
Okay, very good. So do you prefer to have a hat? Some of you do, some of you don't. Okay, we will figure it out as we go. All this, I hope you are starting to get that feeling that all this starts to moving towards this being vector and this being a matrix. Is it? It's not yet clicking, right? It will hopefully click at some point.
May I ask a question?
Sure.
In the previous equation, we said that, as I understand, the probability function of actually we link x with its probability function. But here, do we expect that the probability function of p is psi? If it is not,
Very, very good question. Very, very good question. Brilliant question. So, as I mentioned earlier, we are writing everything in x domain, okay? And in x domain, finding average of x is easy. Just do psi star x psi dx, okay? What you are bothered with is that this is x domain, and can I plug in momentum there? You would be able to plug in momentum if you would represent the same wave function, not in space, but in momentum space. Not in space, but in momentum space. So which is like, you actually can do this. It's Fourier transform of the other one, right? So let's say you go to that space, you represent the same wave function in the momentum space, then this is way easier. Then it's phi star p phi dp. You see? But we are not going there. We keep our business in the space, okay? That's why we want to represent momentum in that space. And when we represent momentum in the x space, it becomes this operator.
So actually, this is not the exact probability function of momentum directly, right? We derive it. We derive this equation. So the actual probability function is phi, right?
For momentum,
Yes.
yes. So probability of being at a certain momentum is this function squared. Being at a certain momentum is that function squared. Okay? But this function squared gives you probability of being at a certain x. Okay? This was a bit advanced. Don't get scared. It was just to answer the question. Okay? Back to our business. Like, we have just discovered that there are operators, right? So in x domain, since we are working in x domain, let me write that down. We will work in x domain, okay? And in x domain, x operator is just x, okay? Vx operator is just Vx. But P operator is this weird thing in X domain. Okay? V is potential. All right? Actually, we can go further. Let me just write down h bar over I del over del x is operator corresponding to linear momentum. Okay? That's our main conclusion here, so let's box it up. Very good. Now that we have that, we can go further and say that all classical dynamical variables can be expressed in terms of position and momentum. Position and momentum. Okay, what does that mean? Let's say you want to find the expected average of some variable. Okay, some classical variable. It could be kinetic energy, could be Lagrangian, could be whatever. Okay, potential energy. But the sentence here claims that every such variable can be represented by position and momentum, right? So what you can do is you can find expected average of any such operation by doing this, by representing that in terms of Q and h bar over I del over del x. So just replace wherever you see x, you replace by x. Wherever you see p, you replace by h bar over I del over del x. Very good. For example, an easy example would be, how do you find the average of potential energy of the particle? Well, you do psi star v of x psi dx. That's it. Does it make sense? Because v of x depends only on x. So you replace x with x, very easy. How about kinetic energy? Do you remember kinetic energy? So you might write it like this, right? But there is a problem here. What is the problem? We want to represent it in terms of momentum and position. So let's go with p squared over 2m. Did it make sense? Yes? So this implies that the operator should be 1 over 2m times, wherever you see p, you just write h bar over I, del over del x, and then you square it. Okay? So kinetic energy is 1 over 2m h bar squared. I squared is minus 1. And del over del x squared is just del squared over del x squared. Do you agree with this? The derivative of derivative is second derivative. All right. What? Yes.
In terms of that equation, the kinetic energy should be an operator also.
Yes.
What does exactly that mean? I cannot understand. So the kinetic energy in classical mechanics represents a number. For example,
Yeah.
this system has this kind of energy in terms of joule for kinetic energy. But in quantum mechanics, we have an operator which doesn't have any meaning and it operates on some operation.
Why weren't you bothered when I said it about momentum?
I'm bothered with you, but I said, okay.
Let's see where it goes, right? Exactly. That's the spirit. Let's see where it goes. So for now, take a leap of faith, okay? And don't forget your question. Let me just write one more thing and we discuss this again. So once I give it as an operator, now I can ask the same question. If I do a measurement of kinetic energy of a certain wave function, of a certain particle represented by a wave function, kinetic energy measurement, okay? What do I expect to get on the average when I do multiple measurements? Okay? What do I expect to get is integral psi of xt with star. Then you just plug in this. Do you see it? I mean, do you see what I did? Yes. I just plugged in the operator, right? So what happened just tells me that if I want to find the average value of kinetic energy, I need to do psi star. I need to evaluate. Okay, let me take out the constants. I need to evaluate this integral. Does make sense mathematically? Yes. But physically not yet. Okay. Okay, but look at what happens, okay? We are going somewhere with this. You see this, right? Now, let me write total energy. Do you remember the name we gave for the total energy before in classical mechanics? We called it Hamiltonian. and Hamiltonian H is kinetic part plus potential part, right? Now let me write down Schrödinger's equation one more time. Don't worry about the hats. I'm just writing the Schrödinger's equation one more time, not doing anything else right now. Do you remember this? This was Schrödinger's equation. Now look at this. I h bar over del t is equal to, let me write it as operators. H bar squared over 2m del squared over del x squared plus Vx psi. Okay, so what is this part? Do you see what that is? If you don't see, let me just point it out. Negative h bar squared over 2m del squared over del x squared is kinetic energy. Do you see it? Yes? So this is kinetic, this is potential. This happens with physics all the time, okay? Things look like this, but then as you learn and learn and learn, they get shorter and shorter. But then again, that short thing represents so many things, right? So here is Schrödinger's equation in full glory. I h bar del psi over del t is equal to h psi. That is what is governing governments. Yes. Yes, definitely. What do you call that operator? Time evolution operator? No, that's something different. Yes. So, but you see, if in case you forget how to write Schrödinger's equation, you now know that it's I h bar on the left side, del over del t, and then on the right side it's just Hamiltonian times psi.
So it's just saying that kinetic energy plus potential is equal to total energy.
Well, it says that the change in the with respect to time depends on the energy. Okay?
So based on this explanation, the changing of psi function, I mean the wave function in time represents the total energy, represents the total energy.
Exactly. Exactly. The higher your energy is, the faster your wave function will move, will change. Okay?
But we don't have any this kind of this description explanation in the classical physics.
Very good question. What is it?
Also, like energy mechanics also can tell us like, yeah, if you say in the above you said dynamical able, instead of dynamical variables you said observables, it will be more clear.
Yes. So
it's actually corresponds to the classical variability. So because the H is an observable, we call it observable because we can observe it in
yeah.
example, and the left hand side also we can observe it in the example. So it's
Yeah, but what it corresponds to in terms of classical intuition?
like conservation of energy.
So what Ekin claims is that this corresponds to conservation of energy. I didn't think about it too deeply, so I won't be able to answer your question now in the high quality standards that I usually answer. But otherwise, this is the equation. It's a very good instinct that you want to connect it to your intuition, right? Because it has been simplified to this. So what is that? Well, to my mind, I think I've been too busy with quantum mechanics. That's why I think I have answers in terms of quantum mechanics, in terms of how wave function rotates and stuff like that, instead of telling you some classical stuff. But
you can also say you can also consider that this
Yeah, that's what I think. That's what I think, which is not classical interpretation. It's not like f equals to ma. That's what he wants to see. Like, he wants me to start from f equals to ma and get Schrödinger equation. No, I mean, I don't need to do that. What is being done is that you can start with Schrödinger equation and derive Newton's mechanics. Okay, so there is a correspondence, but otherwise, I think this is a deeper formula in the hierarchy of things. That's why it might not be so easy to go to the surface structures and back. I mean, it goes this way, not that way, I think.
There is a question in Griffith says that derive the Schrödinger equations from the first principles, and in the parentheses it says that if you do this, put this called Sweden to get your Nobel Prize.
Okay. Okay. Then let's make. Okay, we have 1 more minute. So, from all that we have spoken, and without thinking about it too deeply, let me just tell you that this is the deepest we go. And Ekin is claiming that if you can figure out a deeper law, which is even more mathematical, that leads to quantum mechanics, that leads to Schrödinger's equation, then it will be a game changer. So, who is crazy enough to try to do it? For example, Stephen Wolfram. He is trying to start from mathematics and go up and derive Schrödinger's equation from it. So you can go ahead and watch his Wolfram physics project. It's not done. I wouldn't say that it's done and he just starts with numbers and ends up with Schrödinger's equation. He has just hints at getting something like gravity, something like Schrödinger equation inside his, what he calls it, multi-way systems or something like that. Graph rewriting systems. So there's a graph and there's a rule that rewrites that graph, and it becomes more and more complicated, and at the end of the day he calls it space, let's say. Okay, let's stop here. See you next time.